We're going to continue our discussion of graphing rational functions, which aren't too bad with number line charts, but we're going to look at some more interesting examples. In particular, in this video, we're going to see how sometimes a rational function can actually have a hole in the graph. So let's get into it. We'll emphasize when a rational function has a hole in the graph. So the first example, let's sketch the graph using end behavior, zeros, and multiplicities. Okay, and the function we'll look at is the fraction f of x equals 2x cubed minus 12x squared plus 18x over x squared minus 9. Okay, so we've got this guy here, and we want to graph it using end behavior, zeros, and multiplicities. So it's not factored, so it's going to be easy to get our leading term here. On the top, the leading term is 2x cubed, and on the bottom, the leading term is x squared. So if we reduce that, our coefficient is 2, and x cubed divided by x squared is just x to the first. So our end behavior is based on a leading term of 2 times x to the first, which is like a straight line. So it's going to grow positive on the right and grow negative on the left. So that's our end behavior. Then to get our zeros and multiplicities, we need to factor this. So let's see here. To factor it, on top we could pull out a 2x, which leaves behind x squared minus 6x plus 9. And on the bottom, x squared minus 9 is x plus 3 times x minus 3. And then factoring further on the top, I'll keep my 2x here. X squared minus 6x plus 9 is the same thing as x minus 3 times x minus 3. So I'll call that x minus 3 squared. And on the bottom, we have x plus 3 times x minus 3. Okay, so now it's completely factored. The difference here when you've got a graph that has a hole in it is that when you factor it, something could cancel. So in this case, you can see that I've got a factor of x minus 3 on the bottom and a factor of x minus 3 on the top. So when you cancel those, you're left with 2x times just x minus 3 to the first over x plus 3, okay? So when that cancels, you're left with a hole at the x value that you canceled off. So you can see, like in this version of the function, x cannot equal 3, because if x were 3, our denominator would be 0, okay? However, when you cancel that x minus 3 on the bottom, x can equal 3. That's okay now because the denominator is not 0. The problem is those two things should be equal. So even after you cancel the x minus 3, you don't want x to equal 3. So what we have to do is we have to kind of take a note here of some kind. There's lots of ways to do this, but we have to understand that we're going to have a hole at x equals 3, okay? And when we have that hole, we have to find the y value to go with it, or have some idea of where that hole in the graph is. So if we look at this ordered pair where x is 3, and we plug 3 in there, we can get our y value. So if x is 3, y is going to be 2 times 3, which is 6, times 3 minus 3, which is 0, over 3 plus 3, which is 6. Well, that reduces to 0. So we have a hole in the graph at the ordered pair 3, 0. So we're going to keep track of that as we build our number line chart using all the pieces. So let's set up our number line chart, and then we can build our graph. So there's a couple ways to do this. You could build your number line chart on the simplified version of the function after you've canceled, or you can use the unsimplified version of the function. I recommend using the unsimplified version of the function so that you don't forget here to use the x value of 3, because sometimes that cancels out completely. So I'm going to use this factored version to generate my number line chart. So my zeros are -3, +3, and 0. So -3, 0, and then +3. -3 comes from x plus 3, which only shows up once. So that's multiplicity of 1, which is odd. 0 comes from x, which only shows up once, so that's an odd multiplicity again. 3 shows up 1, 2, 2 times on top and 1 time on bottom, so that's a multiplicity of 3, which is an odd multiplicity. Okay? And before I forget, I'm going to take note that at 3, my graph will have a hole at the ordered pair 3, 0, okay, at the x value of 3. If x is 0, my numerator is 0, so the whole fraction outputs 0. And if x is negative 3, my denominator is 0. So there I'm going to get a vertical asymptote at x equals negative 3. Let me create some space here to kind of separate this from everything else. So the only new thing here is the hole from canceling one of the factors. Now, let's get our signs. So my left end behavior is below the x-axis, so I get a negative output. My right end behavior is above, so I get a positive output. Then use multiplicities. I've got an odd multiplicity, so my output sign changes from a negative to a positive. Odd multiplicity, so my output sign changes from a positive back to a negative. Odd multiplicity, so my output sign changes from a negative back to a positive. Now I have enough to piece together a sketch of the graph of this function. So I'll label my x values negative 3, 0, positive 3. I'm going to go ahead and put the hole in the graph at the ordered pair 3, 0. I'm going to put my vertical asymptote at x equals negative 3, and I'll put my intercept at 0. Now I want to reference my end behaviors again, so I make sure to get those right. So on the left side of my graph, my outputs are below the x-axis, and my left end behavior is like this straight line. So as I move closer to my asymptote, I have to stay below the x-axis and deflect to negative infinity to stay below the x-axis as I get close to my vertical asymptote. Between negative 3 and 0, my outputs are above the x-axis, so I have to deflect to positive infinity as I approach it. Between 0 and 3, my outputs are below the x-axis, so I'm going to drop below. I don't have an asymptote now, I have a hole, so I'm going to come up and stop at the hole in the graph. And then after 3, my outputs are above the x-axis, and I have to have the proper right end behavior, so I have to grow to the right like a straight line. So to the right, my graph's going to do this kind of thing. And so there's a sketch of a rational function with a hole in the graph. Let's try another one that's a little bit different, where when you cancel the factor disappears completely. In this problem, the factor was left in the numerator. Sometimes that can happen. Let's take a look at what happens when the factor disappears completely. So sketch the graph using end behavior, zeros, and multiplicities. Okay. And the function now is g of x equals the fraction where the numerator is negative x squared times the quantity x plus 1 times the quantity x minus 5, and the denominator is the quantity 3x plus 2 times the quantity x minus 5. Okay? And so we'll take the same approach we did last time, except this guy's factored, so we can go ahead and simplify it. I can cancel the x minus 5s to give me negative x squared times x plus 1 on top, and on bottom just 3x plus 2. I don't even need parentheses around that anymore because it's not multiplied by anything with the x minus 5 canceling completely. So you can see the x minus 5 is gone like it was never there. So we have to make a note that x cannot be 5, meaning our graph is going to have a hole at x equals 5. And we need to find the output where x is 5 to find out where the hole is. So we have to plug x equals 5 back into this because we can actually plug it in here. So if x is 5, we get the ordered pair 5, comma, the y value would be negative 5 squared is 25, so we get negative 25 times 5 plus 1 is 6 over 3 times 5 is 15 plus 2 is 17. So we get a hole in our graph of the ordered pair 5, comma, negative 150 17ths. And honestly, I don't really care what the value is. I like to know that it's a negative number. Okay, that might help us out later on. Now we can go ahead and set up our number line chart with the zeros and multiplicities. And again, I'm going to look at the unsimplified version of the function so that I don't forget about that x equals 5 on my number line. So my zeros are 0, -1, +5, and -2/3. So let's see here. -1 comes first. Then we've got -2/3. Then we've got 0. And then we've got +5. So -1 and -2/3 both have odd multiplicities of 1. So I'm going to mark those as odd multiplicities. 0 has a multiplicity of 2. So that's an even multiplicity. 5 has a multiplicity of 1 on top plus another 1 on bottom. So that's an even multiplicity of 2. All right. So those are the x values. Now, we know that at 5, our graph's going to have a hole at the order pair 5, comma, -150/17. Okay. -1, let's go through the other x values. -1 was from the numerator, so its output is going to be 0. -2/3 was from the denominator, so it's going to have a vertical asymptote at x equals -2/3. 0 came from the numerator, so our output is going to be 0. Now we just need the signs between our critical values. To get those, we need our end behavior, so we need our leading term. On the top, my leading term would be -x² times x times x. So on top, I get -x⁴. On bottom, my leading term would be 3x times x. So that's 3x². So reducing that, I get a coefficient of -1/3 times x⁴ divided by x² is x². So my end behavior is going to grow in the negative direction on both sides. Utilizing that, I can see that my outputs on the left end is negative and on the right end is negative. Using multiplicities, we can get the rest of the signs. Odd multiplicity, so my sign changes. Odd multiplicity, so it changes again. Even multiplicity, so it stays the same as it was. Even multiplicity should stay the same, and it does, so that's good. Now we can set up our graph. At -1, we'll put it over here, I get an intercept. At -2/3, I get a vertical asymptote. At 0, I get an intercept. And at 5, I get a hole in my graph at some negative value. Okay, so yeah, we can put that somewhere down here. You can label the y-axis with that value if you like, but again, this is just a sketch. Now, we're going to graph each region. So to the left of -1, my outputs are below the x-axis, and I need this kind of end behavior, so I'm going to have to do that. Between -1 and -2/3, I have positive outputs, and I have to deflect to positive infinity then near my asymptote. Between -2/3 and 0, my asymptotes are below the x-axis, so I'll start here at 0 and deflect to negative infinity as I get close to the asymptote. Between 0 and 5, I've got negative outputs, and I have to hit the hole in my graph over here, so something like that. And then from 5 on, I have negative outputs, so I have to stay below the x-axis and exhibit this kind of end behavior, so I'll simply curve in that direction. And there's a sketch of this function that has a hole in the graph.